Hey math friends, this is AP Calculus section 1.3 notes. In this section, we are going to be exploring graphing calculators as a tool to help us with functions in mathematics. Some of you may have had some experience previously with graphing calculators, and for some of you this may be new knowledge. And either way, that's okay. I'm going to go through it with you step by step. So if you have your own graphing calculator, now would be the time to pause the video and dust it off, get it out, get ready. If you don't have a graphing calculator, unfortunately, I don't have a lot of options for you other than to just follow along at this time. And hopefully you're looking to get one either through ordering one online, buying one in the store, maybe borrowing one from an older sibling, younger sibling, friend, neighbor, whatever. You can always look online, eBay, Craigslist, Marketplace. These are places that you could possibly pick up a used one. If this is an issue for you and you are unable to get a graphing calculator, please let me know, okay? And we can try to work that out. All right, one other option, and unfortunately this is only an option if you have an Android phone. But if you have an Android phone, there is a free emulator. It's the wabbit.emu. If you just go to the App Store and you look, you can download that one for an Android phone, and I know that that is free. It unfortunately no longer works for the Mac operating system or for a Windows operating system. They just don't have it available anymore, but you can, I believe, still download that for an Android phone. I think that there is a TI graphing calculator app for Apple phones. However, it is not free. So that's another option for you as well. All right, getting started. Okay, let's take a look at our first example. We're going to begin by talking about viewing rectangles. So when you are looking at a graph, you are going to choose a viewing rectangle to view your graph, meaning how big is your x-axis going to be, how big is your y-axis going to be. So your viewing rectangle is the display window or the viewing screen that we see of a particular graph. Sometimes the default screen, which on the graphing calculator is zoom 6, that is a -10 to +10 on the x-axis and on the y-axis. Sometimes that gives you a misleading picture of the graph. It doesn't show you all the features that you're looking for, or it doesn't show you enough of your picture. So we often have to change our viewing rectangle so that we can focus on specific parts of our graph. Okay, and the way that we write it is we put the x coordinates first and the y coordinates of the viewing rectangle second, and I'll kind of show you that when we do these examples. So before we even go to the graphing calculator, we're going to start with examples A and B by listing what we already know about the following functions, which I think will help us when we try to figure out what an appropriate viewing rectangle would be for our function so that we can sketch a graph. Okay, so let's begin with letter A. F of x equals x squared minus 36 plus 32. All right, so let's start with what we know about this function. Okay, well, I know that it's a polynomial function. I know that it's second degree, so it's quadratic. And hopefully you remember that quadratic functions, when you graph them, make parabolas. I know, based on what I know about polynomial functions, that my domain is going to be all reals. I know my y-intercept from the equation. The y-intercept is always the constant term, so my y-intercept is going to be big. It's going to be 0, 32. So I'm definitely going to have to adjust my viewing rectangle if I'd like to see my y-intercept on the graph. I don't know what my vertex is because this equation is in standard form, not in vertex form, but I can find it. Hopefully you remember how to find the vertex of a parabola. There's a little formula. You take the opposite of b over 2 times a. That gives you your x coordinate. Okay, so x is going to be equal to the opposite of negative 36 divided by 2 times a, which is 1. So I end up with 36 over 2, which is 18. So the x coordinate of my vertex is 18. To get the corresponding y value, I just have to plug 18 in for x in my equation. So the y value is going to be 18 squared minus 36 times 18 plus 32. I can't do that math in my head, so I'm going to grab my calculator and type that in, and that gives me negative 292. Okay, so all of that work tells me that my vertex is 18, comma, negative 292. Wow, that vertex is way down there. Another thing that I know that this is a parabola. I'm going to go back up here, and I'm going to say that this parabola opens up. We know this because the x squared term in my equation is positive. So I'm going to have something that looks like that, right? So now that I have a general idea here, I am going to think about what I want my viewing rectangle to be. So now I'm going to grab my graphing calculator and open it up. And I'm going to go to the y equals button. And if you have anything in there, you can just clear it out so that we're only looking at one thing at a time. And I'm going to go ahead and I'm going to type in my equation, which is x squared minus 36x plus 32. Okay. Oh, I forgot my squared here. My apologies. I just did x2, not x squared. So we backtrack. And I want that to be a squared. Sorry about that. Whoops. Ugh. All right, so I am just going to type in my equation, and my y1 is going to be x, and then right here, this is the button to make your variable squared. If you're going to do a higher power, then you use the caret. We'll get to that eventually. So x squared minus 36x plus 32. All right, so I have my equation in. And now if I just hit this zoom key right here, and then I go down to 6, this is what we talked about before. Zoom 6 is the standard window. That's going to be negative 10 to 10 in both directions. So we know that our graph is a parabola, but here's one point that I want to make about how graphing calculators can be misleading, right? We know that we have a parabola. We know that our vertex is way down at 18, negative 292. So right now, this almost looks like we're looking at a linear function. What we're really looking at is the left-hand side of our parabola, and we cannot see the vertex of it at this time. So the next thing we're going to do is we're going to go to the window key right here, and we're going to adjust our window. Since we know that our vertex is at 18, okay, maybe we want to leave the x minimum at negative 10, but our x maximum, obviously we need to make a lot bigger, because if we want to be able to see the vertex plus both sides of the parabola, then, I don't know, let's just go with 50. I mean, better to be too big than too small. And the x scale then, I probably don't want to leave at 1 because it's going to put a little hash mark for every single digit on the x-axis. So a lot of times what I just do is set my x scale to 0. So that's not going to put any hash marks on my x-axis, and that's okay, because to me that's not really important right now. I don't need to see those. If I was looking directly at the x-axis and I was looking for x-intercepts, that might be more important to me, but since it's not important to me right now, I'm just going to kind of turn that x scale off. And then my y minimum, well, I know my vertex is way down at negative 292. So I'm probably going to put like negative 300 in as my y minimum. And then my y maximum, oops, I have a syntax error here. I hit the minus sign instead of the negative. There we go, there's the negative. Negative 300. And I'm going to put my y maximum at 100. And again, I can come back and I can adjust these numbers if I'd like to. But now I'm going to go ahead and take a look. I'm going to change my y scale also to 0, turn that off basically so I don't have any tick marks on there. And now I'm going to look at the graph. Okay, so now we can see a lot more of the features of the parabola that we care about. We can see the vertex, we can see both locations where it crosses our x-axis, and we can also see where it crosses the y-axis. All of these features are currently included in our graph, which is what we'd like to see, right? So that we know that we're looking at the full picture. So now I'm going to go ahead and go back to my notes, and I'm going to sketch a picture. Sorry, I'm invading the space of letter B here. That's okay. I will make a new screen. So I'm going to sketch a picture of what that graph looked like and identify the important features of the graph. So I had a parabola that looks something like that. And I know that this point right down here at the bottom was 18, comma, negative 292. And I know that this point right here, where it crossed the y-axis, was 0, 32. And so for example number 1, I want to make sure that I write down what my window was. And remember, I said with the window, we always write it the x values by the y values. So I would say my window that I used was negative 10, 250 by negative 300 to 100. Okay, and these are my x values, and these are my y values. And that's all we need to do for example A. Now let's take a look at example B. Just going to create a new page for myself here. Example B, we have the function f of x equals the 4th root of 81 minus x to the 4th. All right, and again, we're going to start the same way with this problem. We're going to start with what we know about this function, because that's going to help us determine the viewing rectangle and whether we're seeing everything we need to see or not. So what we know is that this is an even root function, and it's the positive half of the even root function, okay? So we're going to do a little domain work here next, and we've done this a couple times already this year. So we're going to look at what's underneath that even root, because we know that what's under an even root has to stay greater than or equal to 0. So I'm going to say 81 minus x to the 4th. That has to stay greater than or equal to 0. And hopefully you recognize that we can do some factoring with 81 minus x to the 4th. That is a difference of squares. So that is going to factor into 9 minus x squared times 9 plus x squared. And then the 9 minus x squared is a difference of squares again. So that can be factored down further into 3 plus x times 3 minus x, and then we still have our 9 plus x squared. That one cannot be factored further. Okay, so now this is the scenario that we're trying to work with here, and we have to figure out what x values work for our domain. So the next thing we're going to do is make a sign chart. The values that would make our first factor 0, or the value that would make our first factor 0, would be negative 3. And the value that would make our second factor 0 would be positive 3. And I want to call your attention to the third factor here. And I want you to realize that 9 plus x squared, no matter what we plug in for x, if we're squaring the value, this factor is always going to give us a positive result, right? Because even if we were to plug in negative 2 squared is positive 4, plus 9 is 13. So any negative number inside those parentheses of 9 plus x squared is going to give us a positive result, as well as any positive number. So that factor is always going to come out positive. So when we do our sign charting here, that makes that one easy. So now let's plug in a number smaller than negative 3. How about negative 4? So if we plug in negative 4, and again, I'm plugging it into my 3 factors here, right above my number line. 3 plus negative 4, that's going to be negative. 3 minus negative 4, that's going to be positive. And then my third factor is always positive. So when I multiply a negative times 2 positives, I get a negative for that region. Now let's pick a number between negative 3 and 3. How about 0? Right here I chose negative 4. Here I'm choosing 0 to plug in. 3 plus 0 is positive. 3 minus 0 is positive, and my third factor is always positive, so that region's going to be positive. And then finally, when I pick something bigger than 3, how about if we go with 4, and I plug that into my 3 factors? 3 plus 4 is going to be positive, 3 minus 4 is going to be negative, and my third factor is always positive. Negative times 2 positives is going to be negative. Now, since I want values that make my inequality greater than or equal to 0, remember, I am looking for the positive regions, which is that one right there. So that tells me that my domain, after all that work, Domain with quadratic inequalities is a lot of work, right? So my domain is from -3 to +3, including those endpoint values. All right, and then the other thing that we know based on our domain, based on our function, since we have a positive even root function, we expect the graph to live above the x-axis. All right. So thinking about what this could possibly look like, it's going to be above the x-axis, and it's going to be between -3 and +3 on the x-axis. Okay, that's where we expect to see our function. So now we go back to our graphing calculator, and we need to go to our y equals. We can clear out our last graph here. We don't need that anymore. Now, okay, we need to do a fourth root. So it's probably been a while. There's a couple ways that you can do this on the calculator. My preferred way is to write a root as an exponent. A fourth root is a 1/4 power. So what you can do is you can just use a parenthesis and put the 81 minus x, and then we need a fourth power, right? So caret 4. So 81 minus x to the fourth inside parentheses, and then we're going to raise that, so caret again, parenthesis again, and then 1 divided by 4. So there's my function. The fourth root is the 1/4 power of 81 minus x to the fourth. Okay, now there is another key that you can use here. If you hit this, and I'm going to go second level quit. I'm going to take you to the home screen for a minute here just so I can show you this. If you go under this math key right here, notice that number 5 down right here, there's this x root key. So another way that you could do this, a fourth root, you'd have to hit 4 first. Okay, so you'd have to clear. You'd have to hit 4, and then you'd hit that math key, and you'd hit number 5 for the x root, and see how that gave you a fourth root, and then you could type in whatever your function is underneath the fourth root. And depending on the model of the graphing calculator you have, this may look a little bit different. It may just put the 4 in and then substitute in the x root button next to it. That still means the same as the fourth root. The newer the version of calculator you have, the more it's going to look like mine. Okay, but I just wanted to show you that that's another way that you could put in a root, and you can type it in this way in the y equals screen as well as in the home screen here. But I'm just going to clear this out. We're going to go back to y equals where our function lives. So I've got that typed in correctly. That's half the battle, making sure that you type your equation in correctly. All right, so now again, remember our window is still in there from our previous problem because that never updates unless you change it. So I'm just going to start with a zoom 6. I'd like to always start with a zoom 6. And that's my -10 to 10. So as you can see, there's my function living between -3 and +3 on the x-axis. And it looks like height-wise that the greatest value of the function appears to be 3 there right when x is 0. So what I'd like to do is I'd like to examine the features of this graph a little bit more carefully, but before I do that, I'm going to narrow my window a little bit. So I'm going to go to Window, and since I know that my x values are between -3 and 3, I'm going to plug in -4 to +4 as my x window. So -4 is my x min, +4 is my x max, and this time I'm going to leave my scale at x equals 1 because I don't mind seeing 4 tick marks. That's not going to bother me. And then my y minimum, I'm going to do the same. I'm going to do -4 to 4. Okay, so I'm just going to tighten up my window a little bit, and I'm going to hit graph. All right, now interestingly enough, and this is part of the kind of the pixelation, I guess, I don't know if that's the right term, but of the graphing calculator, it doesn't look like this graph touches the x-axis. Okay, it appears like it sort of stops and hovers slightly before x equals -3 and before x equals +3. However, it actually does intersect the x-axis. Okay, so this is kind of an important thing to notice about another feature of graphing calculators that can be a little bit deceiving. And here's how I know this. Well, first of all, I just know this because of the algebra of the problem, that if we were to solve for our x values, we would get -3 and +3 as solutions to this equation. They are x-intercepts. But another way that you can prove it is if you go to second level calculate, and you just ask the calculator to, we could do one of two things here. We could either do value or we could do 0, but let's do value. So number 1, so I just hit that. And you can ask it for any x value on your graph, and it will give you the y value that goes with it. So if we expect that -3 and +3 are x-intercepts, if I plug in -3, it should tell me that y equals 0 at that point. So let's try it. X equals -3, enter. Oh, there it is, y equals 0. So now technically the graph doesn't touch the x-axis in those two locations, but it does. It's just that the line gets so close to vertical at that point that the graphing calculator has trouble showing that, and so it just really can't do a good job, so it sort of makes it look like the line stops. And we can do the same thing and prove that we have a value of -3, 0 or +3, 0 on our graph as well. So I'm going to do the value again, and this time I'm going to check +3, and sure enough, at +3 I have an x-intercept as well. So you can use that value for any point on the curve. Let's say right here, I want to know what this point is where this graph is crossing my y-axis. I want to know what my y-intercept is. It sure looks like 3, but I'm not 100% sure that it's 3, so let's check. Okay, I know that the x value is 0 for my y-intercept. So again, I'm going to do a second level calculate, and I'm going to do a value. And I want to know what is the value of the function when x equals 0. And sure enough, it is y equals 3. So based on the information that I just learned, I think I have enough information to sketch a nice picture of my function. So I'm going to go back to my notes. And up here, I'm going to draw my graph. Oops. So I have something that looks kind of like that. Sorry for my sloppiness. And I know that this point right here is 0, 3. I know this point is -3, 0. And I know this point is +3, 0. And it sort of looks, I don't want to call it a half circle because it's definitely not. It's the curvature is definitely not circular. It's more, I don't know, rounded like a root function is, and it is a root function, so that makes sense. Okay, so you might want to make a little note here about how on the calculator it looks like the graph does not touch the x-axis, but it does. And again, that would be a limitation of the graphing calculator that you just need to be aware of. So the tool that we used to figure that out was we did second level, calculate, value, right? And then we just asked the calculator to tell us some of the values that lie on the curve. We did -3, +3, and 0 for our x-axis. When you are graphing trigonometric functions, sometimes you can use the period of the function to choose your viewing rectangle, keeping in mind that whenever we're working with trig, and hopefully you remember this from last year in pre-calc, you always need to make sure that your calculator is in radian mode when you're dealing with trig. So for letter C, we have a function f of x equals sine of the square root of x. Now, I know exactly what sine x looks like, right? That is definitely a periodic function. It has a period of 2 pi, and it repeats forever in both directions. So I have an idea of what this should look like, but I'm not really sure if that square root of x inside of my sine function is going to make my sine function behave differently, and if so, how differently, right? So again, what do we know? Whether it's useful information or not, what we know is that we have a trig function. So we want to make sure that we're working in radian mode. We know that the period of sine x is 2 pi. But the question is, does this function repeat every 2 pi? Don't know yet, right? We also know that we have a composition function. And I don't know if you recall from our notes on functions the other day, but I did tell you composition functions behave strangely. Okay, so let's talk about our domain here. Our inner function, we'll call it g of x, is the square root of x. So the square root of x normally has a domain of 0 to infinity, right? And then our outer function f of x is our curve sine x, which has a domain of all reals, or negative infinity to positive infinity. So if we did the intersection of these two domains, which would be A intersect B, we call that, then obviously that's going to be 0 to infinity. So that is what we are expecting our domain to be. Now, we don't know if it's going to repeat at all in there, but we would expect this graph to live everywhere from 0 to positive infinity on the x-axis. And then the last thing that we should probably think about is the amplitude of our graph, since we have a trig function. And the amplitude of a sine curve is normally +1 to -1 on our y-axis. And the amplitude would change if we had a number multiplied in front of our sine function. Since there's an invisible 1 in front of it, we would expect that our amplitude would be 1. So we'll say amplitude of sine x equals 1, okay? So we expect our amplitude to equal 1 since our a value in front of our sine curve is 1. And again, that was the letter that we used to represent a vertical stretch on our trig functions back in pre-calculus. Okay? All right, so we kind of have an idea here. Let's talk about window. Ooh, and we forgot to do the window on our last problem. So make sure that you go back in your notes and write down that we did a window of -4 to 4 on both our x-axis and our y-axis. But on this one, let's see, for our window, something by something, if our amplitude is 1, then for our y values, -2 to 2 should probably be plenty. But the question is, we don't know what our x values should be, okay? So the only thing that we're going to be able to try is just to plug some numbers in, right? Try some, figure it out, see what happens, see what it looks like, okay? But we know we're going to be graphing something that's going to be starting at 0. So I'm going to go back to my graphing calculator. I'm going to go to my y equals. I'm going to clear out my previous function. And I'm going to type in my new function, which is sine of the square root of x. And your square root button is a second level function right here above your x squared key. So I have to hit second level and then that x squared. And then I have to put in my variable of x. Okay, now be careful. My cursor is still underneath my square root. So if I close the parenthesis right now, it's going to give me a syntax error because technically the parenthesis would be under the radical. So I have to arrow out of that radical. You can see now my cursor is beyond the root. And now I have to close that parenthesis before I can take a look at the graph. And before I do, I am going to go to my window first. I am going to change my y minimum to -2. Make sure you use the negative, not the minus. And my y maximum to positive 2. Okay, so that's going to be my amplitude. I expect it's going to be from 1 to negative 1, so that should be plenty. But now the question is, what should we look at for the x-axis? Well, I know that my minimum is going to be 0, so maybe I'll look at negative 1, just so that I can see and kind of show that the graph starts at 0 where I expect it to start. And then for an x maximum, I'm not sure. So how about if I just start with 10 and we'll take it from there? So I look at my graph. Oh, okay. Well, it definitely starts at x equals 0 like I expect. But if this is supposed to be a sine curve, then I am definitely not capturing a full period of this curve because everything here, for the most part, is above the x-axis, and I haven't gone below and come back up, right? So let's go back to window, and let's maybe change that x max to 25 and see what we get. All right, looks like it's stretching out as it goes. That's interesting because the portion of the graph that's above the x-axis is like between 0 and 10, but then the portion that's below, it still hasn't come back and crossed the x-axis yet, and I'm all the way out to 25. So what if I go maybe to 50? See what that looks like. Okay. So I've come back up now, but it looks like it's stretching out again. So I can't really say that this is repeating on any period because it doesn't look like it's consistently covering the same amount of ground from when it begins to when it ends. So let's go crazy here with our window. Let's go big. Why don't we try something like 200? And see what we see. Oh, I should have turned my X scale off. All right, so now we get a better idea. We can start to see that it looks like the oscillations, the sine oscillations, are stretching out horizontally as our X values are getting bigger and bigger. The more stretched out this curve is going to become. So let's take a look at something really big. Let's go like 500, or if you want, you can go 1,000. Yep. All right. So no matter how big we go on the x-axis, we're never going to be able to capture this entire curve. That is the nature of the graph and the fact that it is, the oscillations keep stretching out. So what we can do is just kind of sketch a general idea of what this looks like. We've got our amplitude of 1 and negative 1. It looks like we're starting up here at 1. And I'm just going to show that it's getting more and more stretched out as we go, right? And as far as the window is concerned, you can put whatever you want in there. We did negative 1 to 500 before, right? But if you wanted to take a look at 1,000, let's go for it. Again, you just see that stretching out thing happening no matter how big you go on the x-axis. So let's just make a little note here. The oscillations stretch horizontally as x approaches positive infinity. All right, and for this graph, this is really the best that we can do since we know that technically it's not periodic in the sense that, you know, the shape is repeating, but it's not repeating on the same period. All right, moving on to the next example. It says to graph the hyperbola by graphing the functions whose graphs are the upper and lower branches of the hyperbola. Sketch a picture of the functions and identify your viewing rectangle. All right, so first of all, let's just take a little journey back to Algebra 2. The general formula for an ellipse looks like this. X minus h squared over a squared plus y minus k squared over b squared equals 1. And the center of your ellipse is hk. And the A and the B have to do with the lengths of the, basically like the diameter across the short end and the long end of your ellipse. That's what those A and B's have to do with. And don't worry about it if you don't remember this. It's okay. We're not going to be working a great deal with this equation, but it's just a good reminder. Okay, this is information you had at one time. So if we wanted to make this equation look like that, we could just do a little bit of algebra with it. So we've got our 9x squared plus y squared equals 1. And I know that this is going to look a little bit goofy, but if we're trying to make it look like that x minus h squared over a squared plus y minus k squared over b squared, we need to somehow undo that 9 that's in front of the x squared. But we don't want to divide everything by 9, because if we do that, then our 1 on the other side of the equal sign wouldn't be a 1 anymore. So we're going to do something that looks a little bit goofy. Remember that multiplication and division are reciprocal operations that undo each other. So I could really write multiplying by 9 as the same thing as dividing by 1/9. And that is true. Multiplying by 9 is the same as dividing by 1/9 plus y squared equals 1. And then I could simplify that and make it look like a squared under the x squared by rewriting that as x squared over 1/3 quantity squared plus y squared equals 1. Okay, and then again, back to what we know about ellipses, because our a squared is smaller, this tells us that our x-axis is the minor axis or the shorter axis, and that our y-axis, because it's over 1 squared, which is bigger than 1/3, that our y-axis is our major axis. So if you can kind of picture an ellipse that sort of looks like an egg shape, and it's standing up. Okay, the egg is standing up, it's not laying down. It has its center at 0, 0 because it's not x minus something or y minus something. So it has its center is at 0, 0. So you can kind of picture that egg-shaped ellipse with its center at 0, 0 standing up, and it's taller from top to bottom and shorter from left to right. Okay, so that's what we have going on here. So our domain of our ellipse, just based on the information that we have here, would be along the x-axis from -1/3 to +1/3, and our range along the y-axis would be from -1 to +1. And I'm getting this information from the a values and the b values in the equation. Okay, so we figured out everything that we need to know about what this function is going to look like just using our knowledge of algebra, but from previous courses. But now we're going to look at this from a different perspective. Now we're going to look at it from the calculus perspective. Okay, so instead, let's begin with our equation. Y squared plus 9x squared equals 1. Oops, I'm sorry. This has a typo in it. There we go. Plus 9x squared equals 1. And if we solve for y squared, then we would get y squared equals 1 minus 9x squared. And then solving for y, we would get y equals plus or minus the square root of 1 minus 9x squared. All right, now graphing wise, we need to have that plus or minus because that's what's going to make the top half and the bottom half of our ellipse. And we'll talk about that when we type this into the graphing calculator in a moment. But let's verify that the domain and the range that I determined before from the general formula for the ellipse is the same as that I would get if I did this using sign charting, which is what we've been doing a lot of lately. So I know that since I have an even root function here, the square root of 1 minus 9x squared, I know for my domain that 1 minus 9x squared has to stay greater than or equal to 0, and I know I can factor that into 1 minus 3x, 1 plus 3x has to be greater than or equal to 0. And the values that would make those two factors 0, again, my CVs or my critical values are going to be x equals positive 1/3 and x equals negative 1/3. So I make my number line with negative 1/3 and positive 1/3. And again, I know I'm looking for the positive regions here. So I do the sign charting that I'm always doing. I'm going to plug something in smaller than negative 1/3. How about negative 1? If I plug negative 1 into my two factors there, 1 minus 3 times negative 1, so that's going to become a positive. That's going to, be a, when I plug something smaller than negative 1/3 in, so let's say negative 1 into my two factors, I end up with, let's see, negative 1 times negative 3, that's going to be a positive plus a positive. So I'm going to end up with a positive here. And then when I plug in negative 1 there, I'm going to get a negative value. So this region right here is going to come out negative. If I plug 0 in, which is in between negative 1/3 and positive 1/3, my first factor is going to be positive. My second factor when I plug in 0 is going to be positive, so this region will come out positive. And then when I plug in something bigger than 1/3, like 1, my first factor will be negative and my second factor will be positive, which will result in a negative region. And again, since I'm looking for the positive region, I can see that my domain is the same as what I determined before. So we still see the domain is negative 1/3, comma, positive 1/3. And then you can play with your y window on your graph to determine your y values. Okay? So now let's take a look at our graphing calculator and let's see what we can see. So again, we're going to go to y equals. We're going to clear out what's there. And we have to enter the 2/2 as two separate equations. So I'm going to do the positive half first. It's going to be the square root of 1 minus 9x squared, which is all under the radical. 1 minus 9x, and then I'm going to hit that squared key right there. Now notice it kept everything under the radical. If you have an older version, then you'd have to close a parenthesis here to show that all of it is being square rooted. And then I arrow out if I wanted to do anything else outside of the radical, but I'm done, okay? So now I'm going to go down to y2 because I have to graph the lower half. So this is going to be the negative half of the curve. So now I need a negative sign, but then everything else is going to be exactly the same. So it's going to be second level square root of 1 minus 9x squared. All right, so now I should have the top half and the bottom half of my ellipse with these two equations combined. The top half will be blue and the bottom half will be red. I'm going to go to my window first because I've still got that huge window in there from my sine curve. And since I knew that my domain was negative 1/3 to 1/3, how about if I just go negative 1 to positive 1 on my x-axis? And I'm not sure, I mean, I know from my algebraic work that I expect my range to be negative 1 to 1. So how about if we just leave it at negative 2 to positive 2 for our y min and our y max? And let's take a look at the graph that we get. All right, there you go. Again, the graphing calculator has a little bit of trouble with anything that's curved, like circular or ellipse shaped, just so you know. So this looks more circle-ish than it actually is, but it definitely has that more of an egg shape. So let's show a picture of what this graph looks like. All right, so we have our ellipse, and if this is 1 in every direction, then x equals 1/3 is going to be about right there and right there, right? So this is kind of where it crosses our x-axis. Up here at positive 1 and negative 1 is where it crosses the y-axis. And we have something that looks kind of like this. And so then we can write down some of these ordered pairs. This is 0, 1, 0, negative 1. This is 1/3, 0, and negative 1/3, 0. Okay? And again, you might want to put a little note for yourself when you're looking back at your notes. to see both halves of the ellipse, you have to graph y1 equals square root of 1 minus 9x squared, and y2 equals negative square root of 1 minus 9x squared. Example 3 says, use your calculator to graph the two functions, then calculate the intersection, and it says intersections in parentheses because there may be more than one depending on the problem, to find all solutions. Sketch a picture of the functions and identify your viewing rectangle. All right, this is a great problem for me to be able to teach you something that is going to be so useful for the rest of the year in this course. All right, so first of all, we are going to do method number 1. I'm going to show you 2 ways to do this problem. So we're going to call this method number 1, okay? And method number 1, the idea here is that both of these, the square root of x and x cubed minus 1, are functions that we know how to graph. Okay, so you could think of it as y1 is the square root of x, and y2 is x cubed minus 1. Okay, and based on that, I can actually, I know what these functions look like exactly. Like, I can graph them perfectly without the aid of my graphing calculator at this point. It's not even needed. All right, so my y1, which I'm actually going to do the square root of x in blue, has a point at 0, 0, a point at 1, 1, a point at 4, 2, a point at 9, 3. So this is what the square root of x looks like. And then my second curve, which I'm calling y2, which is x cubed minus 1, that's my standing snake, but it has a shift down 1. So instead of being at 0, 0, it's going to be at 0, negative 1 with a point right there and a point right there. And so this curve looks something like this. Okay, my job was to calculate any and all intersections. Well, based on what I know about these two functions and the shapes and characteristics of these functions, this point right here, where these two curves intersect, that point right there is going to be my one and only intersection, okay? I just have to figure out where that point is. Where do they cross each other? All right, well, let's jot this down. Hang on. And what skills have I already taught you on the calculator? Well, you know how to graph these two functions. You know how to graph them both on the same screen. And there is a calculate intersect feature on the calculator. So let's see, second level, calculate intersect is what I am going to want to look at, which intersect is number 5. Okay? So let's do that. We're going to go to our graphing calculator. We're going to clear out our ellipse stuff. We're going to go to y1 and put in the square root of x, second level, square root of x. We're going to go to y2 and we are going to put in x cubed minus 1. Oops, I made a boo-boo there. X cubed, I forgot to arrow out of my exponent. Good lesson right there. X cubed minus 1, okay? And I'm just going to do a zoom 6 window on this, negative 10 to 10. And there we go, okay? Which looks exactly like the picture that I drew. And so now I want to know where these two curves cross each other. The calculator will do it for me. So I go second level, calculate, and number 5 is intersect. So now notice that it has this little black flashing X cursor kind of thing, and right now it's on the blue curve, which is the square root of X. Your calculator is calling that Y1, and it's saying, is this the first curve that you would like to look at? So you have to hit enter and tell it yes. And then it jumps the cursor down to the X cubed curve, the red curve. It says, is this the second curve that you'd like to look at? Yes, you hit enter. And now it says, okay, I know the two curves that I'm looking at. Do you want me to make a guess? So you hit yes again. And there it is. The calculator has told us exactly the point where these two curves cross each other. And the intersection is at x equals 1.288, if I round, comma, and y is 1.135. Now I'm going to go back to my notes, and I'm going to write that down. So my intersection was at 1.288, comma, 1.135. And again, just to kind of make some notes over on the left-hand side, that when I do this, it asks you, is this the first curve? You hit yes. It asks you, is this the second curve? You hit yes. And then it asks you to make a guess, and you hit yes. That's the process on the calculator. And the guess that it made is our intersection point, that 1.288, comma, 1.135. And I do want to call your attention to the fact that the x value is the solution. That's always what we're talking about when we're talking about solutions, as we are talking about x values. All right, so that was method 1. Now let's take a look at method 2. Okay, and we're doing the same problem, but I'm just going to show you a completely different way to do it. Still using the graphing calculator as a tool. So method number 2, we are going to set the original equation equal to 0, and we're going to find the root, which is the x-intercept of the graph. Okay, so the graph is going to look completely different. We're only going to have one curve this time. Let me show you what I mean. So we're starting with the square root of x equals x cubed minus 1. So if I were to set this equal to 0, I would have to subtract that square root of x over to the other side. So I would have x cubed minus 1 minus the square root of x. The order of the terms does not matter as long as you have the sign of the terms correct. So now, if I plug this in my calculator, 0 is where y goes. So this would be y equals x cubed minus 1 minus the square root of x. And this time, my solution will be the x-intercept of the graph, and this should be the same value, which was x equals 1.288, found in method 1. Okay, so let's verify that this is true. So we go back to our graphing calculator, go to our y equals. We're going to clear out the two equations that are in there. And under y1, we're going to put in x cubed, show you arrow out of your exponent, minus 1 minus the square root of x. Make sure you have all your terms correct. And we'll leave our window at negative 10, 10, and we're going to graph it. Okay, so again, we only have one curve, not two. We have something that looks completely different. That's fine. So let's sketch a little picture of what we have here. We have something that looks like that. And we have some point right here where the graph is crossing the x-axis. So we want the calculator to determine that for us, and hopefully it's the same x value that we found before. So we're going to go second level, calculate, and this time we're going to do 0. 0 and x-intercept mean the same thing. Those words are synonymous. So we're going to do number 2 for calculate the 0. So now this is a little bit different. We have to tell it where we want it to look. So right now the calculator is asking us for a left bound, meaning they want the flashing cursor to be on the left-hand side of the x-intercept, anywhere on the left-hand side as long as it's on the left-hand side. And to move the cursor, you just use the left and right arrows. So I can move it a little bit closer to the x-intercept, but I can say, okay, right here, I'm going to hit enter, and see it pops up a vertical line right there. And it's going to trap the 0 or the x-intercept between two vertical lines. So now it's asking for the right bound. So now we have to move the cursor past the x-intercept, above it or beyond it, on the right side of it, and we hit enter. And so now you can see those two vertical lines. My crossing on the x-axis is right between those two vertical lines. So now it says, should I make a guess? And you hit enter again. And look at that. 1.2875, which is our 1.288. That is exactly the same as what we had before when we did method 1. So let's go back to our notes, and we're going to put 1.288, 0. So we did get the exact same thing. And how did we get that? Well, we did second level, calculate 0, and then we did the left bound. We hit enter. We did the right bound. We hit enter. And we did our guess. And hit enter. And it gave us that ordered pair, which again was the same answer, that x equals 1.288, that we found in our first method. So both of these are effective ways of solving an equation that has two functions in it. You can graph them separately and calculate the intersection, or you can set it equal to 0 and calculate the y-intercept or the root, or excuse me, the x-intercept or the root.